Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last couple of lectures, we learned about the numerical methods that can be employed in the optimization to reach closer to the optimum solution. In these two lectures, we learned about four methods of the bracketing which are actually part of the elimination methods. Now in these four methods, if you recall, there were two methods like unrestricted search with fixed step size and exhaustive search. In these two methods, we could actually have the precision over the bracket which we want to intend. However, if we are starting from far off from the optimum solution, then it would have taken longer time to reach to the optimum solution. On the other hand, the two other methods we described, which was unrestricted search with accelerated step size and bounding phase method, these two methods can reach reasonably faster closer to the optimum solution even though we start far off from that optimum solution. However, if we start far off from the optimum solution, the precision is not going to be great once we come closer to the optimum solution. So there is a concern with the precision which we are going to get, or a concern we have with the speed or the pace we are reaching towards the optimum solution. And if you recall, for this reason, basically we can use these methods, the four methods we described so far, just to come closer to the optimum solution and bracket it reasonably well so that we can employ other optimization techniques or other optimization methods which can help us get closer and very near to the optimum solution. So today we are going to discuss a few such methods which are also known as region elimination methods. In total, we'll be discussing four such methods. Today we will discuss two, and in the next lecture we'll discuss the other two methods. So let's start with the couple of region elimination methods. The core region elimination concept lies within the fundamental region elimination rule. So first, let us discuss about the fundamental region elimination rule. In the optimization problem using the numerical method, we said our functions are supposed to be unimodal functions. So in case of unimodal functions which has only one optimum solution, either it's the minimum or the maximum, we know that if we progress from one side of the function to the other side, either the function value is going to reduce or increase depending on the type of function. So if we can compare the function values at three different locations, then we can reasonably say which direction we are heading. So we are going to use that fundamental property to eliminate certain region and use it for the methods we are going to describe in this region elimination method. So for example, if you are looking into a minimization function and we are trying to find out the function values at three different locations, location 1, location 2 and location 3, whereas my boundaries are here and here. Within this, if we try to see the function values could be of this nature. On the either side of the middle point, the function values are higher. whereas at the middle point it is comparatively lower compared to the two bracketing or 2 points which is on either side of the middle point. In this case, it is obvious or it is very clear to us that in case of a minimization problem, my optimum solution is going to lie between these 2 points, as the middle point or the point in between these two location is yielding lower objective function value, and hence the function, if it looks like this where the minimum is somewhere here, or if it is something like this, the minimum could be here. So in this case we can reasonably or we can logically say that my optimum solution is not going to lie outside the 2 points which we had considered, which means the area which I am hashing is not going to have the optimum solution, and hence we can actually eliminate these two regions and concentrate our search between the 2 points here, which means we are moving our boundary in these two directions and eliminate certain region of the search space. Another condition can happen where we find that the objective functions are reducing as we move ahead from the left side to right side. In this case we have 3 points, number 1, number 2 and number 3 point. These 3 points, the objective function is actually reducing. If we come to this situation, we can clearly say that the optimum solution in case of a minimization problem is not going to lie any point beyond this middle point. So logically we can say that the portion beyond this middle point on the left hand side which I am hashing is not going to have the optimum solution, and we can eliminate this region and concentrate our search between this point and this point. So we are choosing again the previous boundary on the right hand side and the new point which is here, so that if my optimum solution is somewhere here it is covered, or if it is somewhere here still it is covered. And once we reasonably reduce our search space, we can continue with this process again and again to come closer and closer to the optimum solution, and we continue with this method until we reach the precision level we want. So one of the criteria of region elimination method is to establish some precision level which we want to intend and which is going to tell us how closer we are to the optimum solution. As I said, in the real world engineering problem, we may not always look for the exact solution considering all the variability. Rather, we would like to come very close to the optimum solution which is reasonably good enough for our design or for the problem we have adopted. Now, this concept of region elimination which we showed for the minimization function is going to hold true for the maximization function with similar logic. With this understanding, we'll move on to the two methods which we are going to discuss in today's lecture. So the first method we are going to discuss about the interval halving method. So in this interval halving method, we are required to evaluate the function at 3 different points within a predefined search interval, and these points we are considering as equidistance from each other. And once we find out the objective function at these 3 points, then we can eliminate the region which is not of our interest based on the fundamental region elimination rule we just discussed. Now, when we are choosing 3 points, it is very clear that with these 3 points, we are dividing the search space into 4 equal regions, particularly when our points are of equidistance. So, if we know this, let us look into the precise algorithm which is used in the interval halving method. So in this algorithm, first of all, we find the lower and upper bounds using one of the elimination method. Otherwise, if we already know this upper and lower bound, we use that and find the middle point within the boundary and compute the function value at that location. Then we look into the 2 quarter interval points on either side of the middle point and find out the objective function value at those 2 points. Now we'll be looking into the fundamental region elimination rule to eliminate certain region. So first of all, we are looking into the algorithm for the minimization problem. So if we find the objective function at the first point, which is on the left hand side of my middle point, is lesser than the objective function at the middle point, and which is also found to be lesser than the objective function at the point which is right of the middle point. In that case, we can clearly say my upper bound can be moved to the middle point. So in this case, if we look into the objective function and we are looking into the objective function values at 3 points, which are here and here, and as we can see, our objective function is reducing in this region. So this is my boundary A and B. We can reasonably say that our optimum solution is not going to lie in this hatched region, and hence we are removing this and we are moving our boundary, the upper boundary, to here. So for this reason, we are saying B becomes the new boundary which will take the value of my middle point, and the x1, which was the left hand side point of my middle point or the first quarter interval, that becomes my new middle point. So this way I already know the function value at this middle point. I do need to calculate 2 other points in the next iteration, which is going to be at this quarter and this quarter. So which we'll discuss in the next iteration once we get into that. The other condition could be when the function value at the point which is on the right hand side of the middle point is lower than the objective function value at the middle point, and which happen to be even lower than the objective function value at the point which is on the left hand side of the middle point. So this is going to be the reverse of the case which I have explained earlier. In this case, my objective function value is going to be like this, where my boundaries are going to be here, A and B. This is my middle point, xm. This is x1. This is x2. So we can clearly see our objective function value is reducing in this direction, and logically we can eliminate this region, and hence my new boundary is going to move to the middle point. So we are saying the middle point xm is going to be the new boundary. A is set to the xm, and my middle point is going to move to the point which was there on the right of the middle point, which is x2. So xm is equal to x2, and once we set this, we find the two new points in the next iteration, and the process continues. If neither of this happens, then basically we are saying that the objective function at the middle point is lower or lesser than the objective function obtained at the 2 points on either side of the middle point. In this case, the objective function is going to look like this, where these are my boundary conditions or boundary values. This is my middle point, this is my second point, and this is my first point. So in this case, we are saying that the middle point objective function value is lesser than the 2 points on either side of it, and hence logically we can eliminate this portion, and hence my boundary A moves to x1 and B moves to x2. So that is what we are saying. In this case, my new boundary on the left hand side, or the lower boundary, will take the value of x1, and the new boundary on the right hand side, or the upper boundary, is going to take the value of x2. We are going to retain the value of xm because that is still going to be in the middle, and we have to find new x1 and x2 and continue the process. Now in this process, once we reduce our boundary, we are saying that the optimum solution is going to lie within the new boundary, and hence if we can find out that our new boundary is within our threshold precision level, then we can terminate there, or else, as I said, we have to move to the step 2, which is here, and continue the process. In this process, we are again finding out the new 2 points, which is x1 and x2, for the revised boundary, and we continue the process until we meet the termination criteria. So let us look into this algorithm through an example. In this example, we are choosing this particular objective function to minimize within an interval of 0 and 3. So we know the interval in this case, and we also know the precision which we want, which means the final solution should be within the precision level of 0.2. So first let us look into the middle point, which is very simple. We know the upper limit and the lower limit of the search space. From there we know what is my middle point, and we find out the function value at that location. Once we find out the function value at that location, we move to the step 2, where we are finding the other 2 points, which is x1 and x2. and we are finding the objective function values at x1 and x2. Now once we know this, we are comparing and eliminating certain region, and we are also checking whether my new boundary is going to be within the level we had decided for as a precision, which is 0.2. If not, we continue the process again and again until we reach there. So if we have to solve this problem, we can see the results in a tabular format. So as I said, this is my objective function, my interval, and the precision level we intend to achieve. So now we know the lower boundary is 0.0 and the upper boundary is 3.0 and our middle point is 1.5. The first quarter point is 0.75 and the second quarter point is 2.25. We find out the function values at these three locations. When we compare these three locations, we can clearly see that the function value is lesser at the middle point as well as the second quarter point on the right hand side of the middle point. So we can clearly say that the region from the lower boundary to the middle point is not going to have the optimum solution. So we can eliminate that, and hence my new boundary or the lower side is going to be 1.5, which is the middle point, and my new middle point is going to be the second quarter point, which is x2. That means xm is going to be 2.25. We find that the precision at this point is going to be about 1.5, and since this is higher than the precision level which we want to achieve, we need to move to the next iteration. So in the next iteration, as I said, my lower boundary is 1.5, my upper boundary is still 3.0, and then the middle point we said 2.25, and we compute the first quarter point and the second quarter point, and then we find the function values at the first quarter point and the second quarter point. The function value at the middle point was already known to us, which we have it here, and as we compare the three function values, we can clearly see that the function values are improving if we are moving in this direction. So we can say that the optimum solution is not going to lie until we reach the middle point. We can reasonably eliminate the point up to 2.25 and any point higher than that. Hence we are revising the upper boundary, and we are saying the upper boundary is now going to be 2.25. My new middle point is going to be x1, which is 1.875, and the precision at this revised boundary is going to be 0.75, which is higher than the precision which we want to achieve. Hence we need to move to the next iteration, and in the next iteration my revised boundary is 1.5 and 2.25. Within this, the middle point is 1.875, the first quarter point is 1.687, second is 2.062, and the function values are indicated here. Again, if we compare the function values at this level, we can clearly see that the objective function values are reducing as we go from x1 towards x2. Hence, we can logically eliminate up to the point xm, or the middle point, and revise our boundary, the lower boundary particularly, to a equal to the middle point, which is 1.875. Revise the middle point and then look into the precision, which is still higher than the precision value which we want to achieve. Hence we move to the next iteration, and as we move to the next iteration, we find that my revised boundary, the lower boundary is 1.875, the higher boundary is 2.25, and the middle point is 2.062, first quarter point is 1.968, and second quarter point is 2.156. When we evaluate the function values at these 3 points, it is very clear to us that the function value is reducing towards x1 when we move from x2, or rather we say the function value are increasing if we move from x1 towards x2. So we can eliminate the region which is on the right hand side of the middle point xm. So we can eliminate that region, and once we eliminate, my upper boundary is going to be the middle point, which is 2.062, and new middle point is going to be 1.968, which is x1. And at this point, after revising the boundary, we can see that the optimum solution precision is going to be 0.187. In this case, the precision is based on the design variable values, so which is within the range which we have chosen. Hence, we are terminating the process at this point, and we are reporting that the optimum solution is going to lie between the lower bound, which is 1.875, and the upper bound, which is 2.062. And if we average it out, basically we are saying that the optimum point is going to lie very close to the middle point, which is 1.968, and expected optimum function value is going to be very close to negative 49.945. So it helped us to reach the optimum point, and if you try to solve using the classical method, you will find that the optimum solution is possibly at the point 2.0, and we are very close to that. So we should be satisfied with this solution unless we want to revise the precision. Now, another thing to notice about this particular method is that in the first iteration, we evaluated 3 functions. In the second iteration, we already had 1 function value from the first iteration, so we evaluated 2 functions. In the third iteration, we evaluated again 2 functions because we already had 1 function value from the previous iterations. And in the last iteration, we again evaluated 2 function values, as we retained one of the function values from the previous iteration. So in all together, we evaluated 9 function values. So as we go and look into the methods, it is important to see how many function values we need to evaluate in the process. So keep this value in mind. We'll be using the same objective function and the same interval and the same precision in the other methods which are coming up, to see how many function evaluations we need to do to come closer or come to meet all the requirements. So as I said, in this case we are evaluating the function values 9 times to come to the level of precision we had chosen. Let us look into this solution in a graphical format. In this graphical format, you will see that our initial boundary was 0, 0 and 3.0. We had selected the middle point, which was 1.5, and the first quarter point was 0.75, and the second quarter point was 2.25. When we compared the function value, which you can see it clearly that the function value is reducing as we move from left to the right. So we can reasonably say that half of the region, which is up to 1.5, we can eliminate. So we eliminate because the optimum solution, in this case the minimization problem, the optimum solution is not going to lie on the left hand side of this middle point. Now as we eliminate, my new boundary is going to be here, and we are retaining the old upper boundary. Then my new middle point is going to be here, which was the x2 in case of the previous iteration. And now we have to find out the two other points, which is the first quarter point. One is going to be at 1.875, which is here, and the other is going to be 2.625, which is going to be here. Now at these three locations, once we find the objective function value, it is very clear to us that the objective function value is reducing as we move from x2 towards x1. Again, looking into the fundamental region elimination rule, we can clearly say that up to this middle point we can eliminate the region on which is there on the right hand side of this point. As we eliminate this region, my new upper boundary is going to move, which is going to be the new point is going to obtain the value of the middle point of the previous iteration, and the x1 point which was there in the previous iteration is going to be my new middle point. And then we have to calculate the two other quarter points. One is going to be 1.687, which is here. The other is going to be 2.062, which is going to be somewhere here. Now again, if we look into the function values very closely, we'll see that the function value is reducing in this direction, and it is continuously reducing till we reach the second quarter point. Hence, as per the region elimination rule, we can eliminate the region which is there on the left hand side of the middle point. Once we do that, my lower boundary is going to move to the middle point, and my new middle point is going to be the x2 point of the previous iteration. Then we calculate the two quarter points. The first quarter point is here, the second quarter point is here, and again when we compare the objective function values at these 3 points, we will find out that the objective function values are reducing as we move from x2 towards x1. So it is reducing in this direction, and hence as per the region elimination rule, we can eliminate any region which is on the right hand side of the middle point. And as we eliminate this, my upper boundary is going to move to the middle point of the previous iteration. So now my optimum point is going to be within this region and the middle point of that is here, and once we check the range of this boundary, we'll find that it is meeting the termination criteria, and hence we are stopping at this point and reporting the lower and the upper boundary as the boundary values or the boundary values of the objective function, with the middle point as the most possible or roughly the optimum point. So that was about this particular method where we eliminated the region by 50% at every iteration. We could see that at every iteration we are reducing the region by 50%. However, we have shown you that the number of function evaluation required in each iteration is 2, except in the first iteration it was 3. So we also need to find out any method which can improve on the number of objective function evaluation required. In that quest, we can move into the next method, which is Fibonacci search method. Here you will see that the number of function evaluation is going to reduce compared to the interval halving method. Let us understand the Fibonacci search method. So in interval halving method, as we had said, we need to evaluate 2 function values at each iteration, except the first iteration where we had to evaluate 3 function values. Now, instead of introducing 2 new points in each iteration, if we can introduce only 1 new point, then we need to evaluate only 1 function value at each iteration. Keeping that in mind, we are looking into the method where we need to use only 2 points to eliminate the search region instead of 3 points which we used in case of interval halving method. And if we can retain one of the 2 points in the next iteration, then we need to just evaluate 1 additional point in each following iterations, and in that way we can reduce the number of function evaluations needed in the overall process. So the Fibonacci search method relies on that principle and uses the Fibonacci number to do that. Now, Fibonacci numbers are the numbers which represents the summation of the previous 2 number. And if we look into that in a mathematical way, we can say that the Fibonacci number is the summation of the previous and the previous to previous number. And if we represent the series, it is going to be the first number is 1. Since the previous number is 0, so 1 plus the previous number 0 is going to yield the next number as 1, and the next number is going to be 2, because if we add 1 plus 1 is going to be 2. Then the next number is going to be 3, which is 2 plus 1 is going to be 3, and the process continues. We can use this property while identifying the region and eliminating, and if we do this, we'll see that we need to evaluate only 1 function value at each iteration, except the first one where we need to evaluate 2 different function values. So first of all, let us look into one of the basic property of this Fibonacci number. Since the number is the summation of the previous 2 numbers, then we can write that this summation can be represented as 1 with the help of normalizing it based on the present number. This function we'll look into further once we look into the Fibonacci series. So as I had said, the Fibonacci series the present number is the summation of the previous and the previous to previous number. So when we look into just the previous number, that is the summation of the previous to that number and the previous to previous of that number. So here we are seeing that if we keep on decomposing that number, we are going to keep on increasing the fraction. Now once we scale it only to 1, we can say that all these numbers are, if we add, it's going to give us 1 if we divide it by the main number which we are trying to find out. Now if we look into with an example, we can clearly see that if we are starting from the number 8 is equal to 5 plus 3. So we can say it represents this way. Then the 5 is representing 3 plus 2. We are representing it as 3 by 8 plus 2 by 8. And then we have also 3 by 8. Then the 3 is representing 2 plus 1. So here we are representing that 3 as 2 plus 1. We already had 2 by 8. So we have the complete series like this. Then 2 is represented by 1 plus 1. So we are representing that in this way. Now let us look into what exactly can happen. Once we represented the number as 5 by 8 and 3 by 8, then this fraction is same as once we again decompose this number and we obtain this fraction.